And thank you all so much for joining us for the Behind the Material Property Sheet webinar. Like Nick said, I'm Sammy Sadi.
And I'm Stephanie Williams.
So this is the first webinar in a series of webinars. So please stay tuned until the end of this to see the full schedule of all the other webinars and for more information on specific plastic testing applications. So some of you are probably familiar with this image, but this is a material specification sheet. It provides a snapshot of the material's key properties as measured by the manufacturer. These properties are typically measured using ASTM or ISO standards and contain the average value that the material exhibits per the standards method. The spec sheet can be used for various purposes, such as supplier verification or new product development. If you go back one side.
Sorry about that.
Some of the key properties of the material property sheet provide information on the thermal properties such as flow rate and heat capacity, the mechanical properties such as strength and ductility, impact properties that also show the strength and ductility, heat capacity properties such as heat deflection and softening. A materials property sheet is essential for selecting the right material for specific applications based on the performance requirements. Understanding these properties is vital for successful engineering and manufacturing processes and ensuring that the products are reliable and effective in their intended applications. To ensure your plastic is the best material for your end application, you will need the proper equipment to test your material. And luckily for you, Instron has a full plastic product portfolio that will test your plastic at every point in the manufacturing process.
Great. Thank you, Sammy. So looking at the materials data sheet, one of the tests that you need to run is a melt flow test, melt flow rate. So the concept of the melt flow testing is really very simple. You have a polymer, a material in the form of pellets, flakes, or granules that you install into a heated barrel, raise that temperature in the barrel up to the test temperature you want to use, and apply a force to it, and then measure how quickly it flows, what its flow rate is. Why would you want to use this test? Well, if you're a producer of polymers, it gives you a spec sheet to provide to your consumers that give them an idea of how this material should flow. If you're the user, it gives you a reference point that you can look to the spec sheet, see what the data the supplier is saying you should get, and you can run the test and do a quick QC check on it. As well, it can be used to compare new materials to determine quickly which is a better material to use. And it can give a snapshot to determine if the polymer is so suitable for a specific molding application or not. A melt flow test is a very standards-driven test. The ASTM and ISO standards define very well how the test should be done. And in addition, the systems used in these tests are very standards-driven. The standards, either ISO or ASTM, both call for the system to have a heated barrel. That barrel is to be a defined length, overall length, and diameter. In addition to that is the piston itself shall be a defined diameter and length, have certain characteristics such as marking, witness marks on it, as well as the foot or the head of the piston shall be to define dimensions and lengths. In addition, you have the die that's located in the bottom of the tester. This is the part where the extrudate comes through. That die will be a defined overall dimension, an overall length or height, as well that the diameter of the orifice in the die will be defined. You also will need to have a means to apply the force to the material, the extrudate in the barrel, and that shall either be mass or you can use a load cell to apply the force. So we have a variety of people attending this, and I just wanted to do a quick overview of how this test works. We put the die in, add the polymer, put in the piston, apply the mass. Over time, with the force from the mass pushing down on the polymer, it extrudes out. The extrudate is cut during the testing, weighed, and then the calculations made. So melt flow testers, as I said, they're very standards driven systems, but you could have something as simple as a very simple system, such as the one on the left. The system as a manual task, the operator will need to time the task, um, apply the masses manually. It's a good system if you only are going to test one or two materials. You're only going to need to use one or two masses to run those materials. If, however, your lab is more of a R&D lab, or perhaps you do a lot of different materials coming into the lab, you need a lot of different masses, you may want to consider a system more automated, such as the one on the right. These are systems that would have a load cell in addition to an encoder. The load cell would help with compacting materials and purging materials. You may have a mass selector, such as shown here, where you would have the stack of all the commonly used masses in melt flow testing. And you might also have a semi-automated cleaning mechanism or an automated cleaning mechanism to help with the cleanup after the test. Uh, and that may be the best solution for your lab. Test standards, there are two big standards, ASTM D1238 and ISO 1133-1 and -2. There are other test standards that are driven for specific materials, such as ASTM D3364, which is specific to the melt flow testing of a material like a PVC. Within the ASTM and ISO standards, there are different test methods to be used, method A and method B, and in the ASTM standard, we have method C and method D. Method A in both procedures is more of a manual test method, one in which after the mass has been applied, the operator will time and make cuts of the extrudate at a specified time, and then take the extrude, weigh it, and then do the math to come out with the melt flow rate. Method B for both systems and brings in an encoder, and the encoder then watches the travel of the piston, and the test is set up to have the cuts made at either when you reach travel a certain distance, or after a certain time has elapsed, then you've traveled the distance. With the method B systems, you can usually then enter the data, the weight, and it will go off and calculate that data itself. Method C in ASTM is for high flow rate materials. Those are materials that flow at a rate of 35 grams or more, 70 grams or more. And in that case, the die would be different. You would have what we call a half die. It would be half the overall height of the standard die. And you may bring in other options such as a 100-gram piston or mechanical magnetic holder to hold the piston during the test.
Going into the next row of the data sheet, we will talk about the static testing requirements. For the static testing requirements, a universal testing machine is required. It's an electromechanical testing system that is used to mainly test material in tension and compression. It's comprised of a sturdy crosshead that will move up and down, a base beam for stability, a load cell to measure the force of the material, ball screws that help guide the crosshead up and down accurately, a controller to drive the system, and between the load cell and base beam, various accessories and fixtures can be used to perform tests of your requirements. So what type of equipment should you be using for static testing? As identified on the product data sheet, the biggest need for testing on a static system is going to be tension testing. A couple other test types would be compression and flexural tests. Typically, in tension, plastics don't exceed over 5 kilonewtons of force, but reinforced plastics can see 10 kilonewtons or more in tension. A table model system will allow for all the static tests to be ran per the standards and also allow you to add a chamber for temperature testing in the future. The image on the right-hand side showed a dual column system, which was what we call a table model. So that one would be the ideal system for adding a temperature chamber in the future. Looking at some tension tests, what are the most common accessories that we should be using? For all test types, a load cell is going to be required to gather the force readings of the material. Like we mentioned, typically plastics testing will require either 5 or 10 kilonewton load cell. When testing in tension, side action grips or wedge action grips will be able to hold the material without any slippage. It's important to have all of your accessories be rated to a force capacity that's higher than your material strength to avoid damaging any of your accessories. ASTM D638 and ISO 527-2 are the most widely used plastics testing standards. Both of these standards require the use of an extensometer to measure the strain of the material and to obtain a modulus calculation. Both contacting and non-contacting extensometers can be used to record the modulus. The clip-on is the most commonly used extensometer for tension testing, while the AVE or automatic video extensometer is best to use to achieve more accurate and repeatable data without influencing the material throughout the entirety of the test. ISO 527-2 and ASTM D638 have a lot of similarities, but it's best to read the standards very closely to ensure that you're complying. So, a few differences between the two standards for tension tests are going to be the geometry of the material. To not break any of the ASTM or ISO rules, I can't show you those exact geometries, but a few key items to mention is that the only thing that they have the same between the two is going to be the distance between the grips must be set to 115 millimeters. ISO also has shorter tab lengths and is overall longer than the ASTM D638 dog bone. And then in this image here, you can see that the ISO and ASTM gauge lengths are going to be different. So the ISO gauge length is 75 millimeters between the marks, and then for ASTM, it's required to use a 50 millimeter gauge length. ISO also allows you to test with two different test speeds, whereas ASTM only allows you to use one. Overall, ISO has more strict requirements for transducers than ASTM. Um, like we mentioned in the past couple slides, all the extensometers and accessories that we mentioned are compliant to both ASTM and ISO standards, but it is important to know what their accuracy requirements are per the standard. These are all super important factors to consider when testing. If you are testing to both ASTM and ISO standards, testing them in the exact same way will lead to inconsistent and inaccurate data.
Yep. Think.
So just like the tension test, a load cell is required for both compression and flexural tests, and it is required to have a higher capacity load cell than what your material is going to be experiencing. If you're planning on performing both tension and compression testing, it's really important to note that a lot of compression testing of plastics do reach over 30 kilonewtons of force. So a 30 kilonewton system might be the most ideal frame solution to future proof if you're planning on testing compression in the future. For compression testing, a pair of compression platens would be required. So for ASTM D695 and ISO 604, which are the two most important compression testing and plastics testing, those two do require compression platens, whereas the upper platen can be a spherical seated platen to allow for parallelism to be maintained throughout the entire test. For flex testing, Instron's 3 or 4 point bend fixture is required. By simply loading your specimen onto the loading anvils, the crossset of the system will compress the material at 3 different points to perform this bend test and obtain the flexural modulus. For modulus calculation requirements, an extensometer or LVDT, linear variable deflection transducer, can also be used for more precise measurements. The universal testing machine has a modular design that allows for all of these test fixtures to be used on one single frame by just removing the fixture by using a pin and clevis connection. Like we mentioned before, the tensile test, there are a few differences between the ISO and ASTM standards, so please be sure to read these standards thoroughly before conducting any of your tests.
Okay, thank you, Sammy. So the next test we'll go over from the data sheet are the impact tests. These are usually done to either ISO, which is ASTM D256 and ISO 180, or Sharpie, which is actually ASTM D6110 and ISO 179. So in these tests, the polymers are molded into a bar, or well, they're molded into a bar, which then has a notch cut into it. And there are then positioned using a pendulum either on horizontal to the impact plane or vertical to the impact plane, depending on if it's a Sharpie or an ISO test. These tests are widely used for quality control to ensure that materials meet specific standards for toughness and durability, and they can be used as R&D for a quick means to assist in the design of a new material and products by providing insights into the material performance. So some key components to the pendulum machine. They'll all have a hammer or a falling mass. Usually the hammer will be attached to a shaft that is passed through a set of bearings and then has an encoder in the back. They'll have a specimen fixture that's in compliance to the test standard mounted at the bottom of the pendulum, at the base of the pendulum. So the key measurement that we're taking away is the energy absorbed. The machine measures the energy absorbed by knowing at the top release angle. As it swings down through the specimen, it reaches a height on the other side at a different angle. And then we subtract the two angles and then subtract a windage correction factor for the bearings in the encoder that are putting drag on, and we get the energy absorbed value. And what does that look like? Just quickly, as we see in this illustration here, we start at the top height, we release, swing down through, break the specimen that's down at the base, go up to the second height on the left-hand side of the machine, and then compare the values to get the energy absorbed. The common equipment, as I said, is a pendulum here. We have either a manual model version or a motorized version. Most polymers, most common polymers, will fail with impact energies of 5 to 7 joules. In that case, a manual system will usually be sufficient. In this system, the hammer is released and returned to its drop height manually. A brake is applied manually. If you find that your materials are perhaps more heavily filled with glass or fibers or more of a composite material, then you might need a heavier hammer, higher capacity hammers of 11 joules and up. Then we would recommend a motorized system. In this system, a motor will There'll be a pneumatic release. It will let the hammer fall at the start of the test. It'll swing through. It will engage a brake to stop the swing on the second side. And then the motor will engage and return the hammer to the drop height. This system, as I said, is more for heavier capacity hammers, as well as if you have might have a lot of different operators and you want a little more consistency in time of release and making sure that the drop angle is at the same height. Test standards and the types of tests. First, we'll start with a 3-point bend Sharpie test. This is a very common test. It's also a very old test. It actually, for polymers, is a duplicate of a Sharpie standard that was developed in 1905 for metals. It can be run on notched or unnotched specimens. And the standards clearly define that this test needs to be done on a pendulum. The most common standards for this are ISO 179 and ASTM 6110. The sample itself, as you see in the photo to the left or to the right, is a rectangular bar, as I noted earlier, with a notch cut in it. The notch faces away from the direction that the hammer is going to swing in. The specimen is centered across the span of the shoulders that you see based on the notch. Once the specimen is positioned and properly located, the hammer will be released, swing through on the back, be hit on the back side of the notch, breaking the sample, and then you'll get the energy absorbed calculation results. In addition to the energy absorbed, you'll also need to make note of the brake type. These brake types are defined as a non-brake, a partial brake, a hinge brake, or a complete brake. Besides the Sharpie test, probably even more common than Sharpie on a property sheet, you'll find results for the ISO. Similar to Sharpie test, this is a test conducted on a rectangular bar that's notched. In this case, the specimen is oriented in a vertical position with the notch facing the hammer. And again, the specimen is centered on the notch itself. Again, a very common test can be conducted on either a notched or an unnotched sample. An old standard that was developed from the standard created in 1903 for metals has a very unique striker shape. In addition to the unique shape of the striker is the orientation of where the specimen actually gets hit. It actually gets hit above the notch, forcing the sample to bend backwards and tear along the notch. It's really sort of used more as a comparative test, comparison tool. This is in part because of just some issues with the test setup itself, which we'll cover later in the presentation. Again, you would note the energy absorbed values as well as the specimen brake type, and those brake types would be the same as they were in Sharpie: a non-brake, a partial brake, a hinge brake, or a complete brake. The most common standards are ISO 180 and ASTM D256. Another type of impact test that you may find on some data sheets is the multi-axial or high-speed puncture tests. These are to standards ASTM D3763 and ISO 6603-2. Here, the sample is a plaque as defined by the test standard, the size defined by the test standards. And basically, we're subjecting that plaque to a high-speed test with higher velocities and impact energies than are usually prescribed for in the pendulum machine. And we're looking to find a transition from a very ductile, tough material to a brittle material, or we're looking to compare how does any polymer react to a high-speed impact event. Key components to a drop tower, we have a latch that the falling mass is attached to. Attached to that falling mass, we have a flag that will serve as our to provide us with our velocity or speed at which the mass is traveling. We also have a tup or load cell attached to that mass, and attached to that tup or load cell is an insert of a defined size and shape as per the test standard. We have a velocity detector that catches the flag as it passes through. When we have shock absorbers or a means to stop the falling mass at the end of the test. And we also have a fixture to support the test specimens. The way the test is run is the plaque is placed on the fixture. The mass has been defined or either by the standard or the mass that you are choosing to use to run the test with. You go to the drop height, the mass is released. As the mass falls, the flag passes through the velocity detector, triggering the system to collect the speed data, and then usually open a data acquisition system. The top and insert impact the specimen, and the specimen is punctured, and then the falling mass comes to a stop with the shock absorbers stopping it. So all drop towers are essentially the same. They have the same components we talked about. You can have a very simple system, such as the one to the left, which is a gravity system. Once the falling mass is released from the drop height, it's purely a gravity release, a gravity velocity or increase in speed. Or we can add another level of impact energies and velocity, either through the use of pneumatic cylinders or springs to help accelerate the falling mass to reach higher speeds and therefore apply higher impact energies to the sample under test. As well, drop towers can be equipped with thermostatic chambers, so testing can be done at high or low temperatures. They may also be equipped with bigger bases to accommodate larger components or parts that would be under test. Other common parts of a drop tower involve the impacting of the specimen. This would be the top load cell and the insert. The inserts usually defined by the test standard. We'd have a clamping set, an upper clamping ring that would be attached to a mechanism, a set of cylinders to come down and hold the specimen in place between the upper ring and the support ring. Of course, the clamping set has to be supported on a rigid base so that we minimize any deflection given due to the impact event, and we're not bringing that deflection movement of the fixtures into the test event itself. The most common standards, as I noted, are ISO 6603-2 and D3763. And you'll see differences between these standards as into the top insert to be used, the unsupported test area that's with the clamping set. And in the case of ISO 6603-2, there is a call for a lubricant to be applied to the top and the insert between each test. In addition to the tower and the fixturing and the top or load cell, other common equipment is a data acquisition system where the results from the velocity detector come in to give us speed. The results from the load cell or top come in to give us force. And from there, we can calculate displacement and energy at peak. We can also plot how the specimen, the plaque under test reacted to that impact event. And this can then be used to compare results from any material, any one material tested under various conditions, such as higher velocities or lower velocities, higher or lower temperatures, and can also be used to compare, say, two different materials under similar test conditions. So puncture tests, common test, used only for plastics, and they're newer test standards, as you'll know. The puncture test standards came about in the 1990s. The most common ones are ISO 6603-1 and -2 and ASTM D3763. So we move from puncture test, another test on the spec sheet are the heat distortion and softening test, or HDT VICAT testing. Here we're looking to take the polymer and expose it to higher temperatures to see how does it react when it is in a high temperature environment, such as in an engine compartment or in the interior trim of your car, or say electronics. How will these polymers react when they're forced to have to work in higher temperatures? Key components of an HDT VICAT system include the weights, stations, the test head and fixture, a bath that the stations are lowered into, and LVDTs. LVDTs located next to the test specimen to watch the movement of the specimen as it either deflects or softens during the test. Common equipment, the standard practice in these tests is you should be running at least two tests because you're looking for an average. You're looking to average these values to get the result or the value you're going to report. So standard is to run two. If you run three, though, which would be the system on the far left, three tests gives you the two tests to do your average with, but also gives you one test that, in case you get a big difference between the two, you can have the third as the tiebreaker, if you will. So you can decide between the three, the two that are closest, and you're going to average. If you want to run more tests, though, or maybe you want to run both HDT and VICAT tests at the same time, then a system with more stations, up to 6 stations, such as the two you see, the one in the middle and the one on the right, more stations gives you more efficiency in the lab in that you're getting to do more rounds of testing. You can test different materials as long as the temperature and ramp rate are the same between the systems, the material being tested, then having a 6-station system could be more beneficial and more efficient for the lab overall. The key principles, or what are we doing with the test? So with the VICAT test, the purpose is to measure the temperature at which the surface softens enough that a flat-based needle, thin needle, will penetrate, will be able to sink into the softened surface a millimeter. Okay, and the standards for that are ASTM D1525 and ISO 306. HDT testing, we take a beam, is a beam test similar to the Sharpie test or even a flex test on a static system. That beam is positioned over a span, and then we apply the mass on the station and look at when does that beam deflect. And again, it's usually a millimeter that we're looking in deflection. We mark when we see that distance travel on either test, we mark that as end of test and we note the temperature at which that system, that specimen failed. So
Great.
now, nope, Sammy, I think this is yours.
Yeah, sorry about that.
Nope.
We are running a little bit behind schedule, so we're going to run through these challenges as quickly as possible, but still making sure that we have time to answer your questions at the end. But now that we went through the type of systems that are needed for every stage of the plastics process, we're going to go over a few challenges that we face during these tests. But for more in-depth information on the static and pendulum challenges, we will give you the link to Stephanie and I's three challenges of plastics testing webinar that we did last year to give you a more in-depth look into specifically the static and pendulum challenges.
So if I start with melt flow testing challenges, you'll see that where we see the three biggest are getting test results, increasing your lab efficiency, and the testing standards. This slide just shows sort of a compilation of where we see the biggest result issues being. We've highlighted with a yellow ball circle those that we think are the biggest contributors. Of those, I would say making sure you have the right test method. You're comparing test methods to the same one on the result sheet or the one that you're comparing data to. You have that right. Prepare your sample properly. If your specimens are hygroscopic, you need to account for a means to keep the water, the vapor in the air to a minimum. Uh, Cleanup, can't highlight enough. You need to make sure these systems, these melt flows are clean between each test. Otherwise, you'll get inaccurate data. Uh, Increasing lab efficiency, very manual system on the left. This depends on the operator, keeping track of the time, making the cuts at the same time, and doing all the calculations. You can increase efficiency by bringing in automation, such as the motorized lifter to apply masses properly, a load cell to help with compaction and cleaning, and more software to help with the calculations. The biggest challenge is make sure you read your standard. The tests look the same, but the standards themselves have differences in them, and you're going to want to make sure you're following the right standard and the right method.
Going over the three challenges that we typically see with static testing are they're going to sound very familiar. So making sure that we're going to the right test results is the first one. So making sure that you're obtaining the correct test results means that it's important to test in the correct way. So specimen alignment is going to be the most critical point in your test. And then from these images, you can see that this specimen is more and more misaligned. So just by taking the time to visually align this within the grips is going to allow you to get significantly more accurate data. And then something else that will help is just adding something as simple as a specimen alignment device. And then another crucial part of obtaining the correct test results is ensuring you have a preload within your method. So a preload will apply a small load to the specimen before the test starts to remove this circled area in the curve, which is typically called a tail. This tail is actually something that is going to be detrimental to your modulus calculation. So making sure that your preload is set to remove this tail of your curve. Increasing our lab efficiency is something that we're always striving for. Ultimately, the more automated we can be, the more efficient we can be. So, adding something small, such as automatic accessories like pneumatic or hydraulic grips, will allow you to operate and load your specimen quicker. along with adding a automatic X tensometer such as Instron's AutoX or AVE. And then also adding a automatic specimen measuring device that will automatically input your width and thickness uh, uh, measurements to your software will save a lot of time. But also just this doesn't only just save you time, it also ensures that your results are going to be significantly more repeatable and accurate over time. And then lastly, our testing standards. I know we've mentioned this so many times, but making sure that you're being compliant to your testing standards because this is one of the largest areas that we see that will lead to variability within your testing results. So be sure that you're testing to your standards correctly. So read up and on your ISO and ASTM standards.
So challenges for impact pendulums, again, test results, lab efficiency, and testing standards. Key factors that influence impact testing with a pendulum, uh, notching the sample, making sure you have the right test method, you're using the right method, and ensuring that you have the correct hammer capacity are key. The challenges, as we note here, ASTM versus ISO, differences in the standards, read the standards, make sure you've got the right fixturing, the right specimen, you're orienting everything in the right place. Notching, because these tests are dependent on the notch. If you get a good notch, as you see on the left, a nice clean notch, you get good results. If you get bad notches, then that affects the result. It affects the impact energy, the values that are important that you're looking for. To increase efficiency, as I noted earlier, IZOD is usually the most commonly run pendulum test. Instead of a manually tightened vise, think about using a lever action or pneumatic action vise. These will speed up throughput in the lab by speeding up the application of the clamping force of the face on the sample. Notching. Have a good notcher. Have a system that you can notch several samples at one time so that when the notch is cut, it's cut over the same time. Remember, plastics can change. Their properties, impact resistance properties can change over time. So you might want to have a notch with more automation to handle bigger samples. A digital measuring station, one that attaches to the pendulum itself and ports the dimensions in. The standard state, you need to measure each specimen prior to test, especially the area below the notch. HGT and VICAT challenges. Again, our three we're going over. Test result challenges. Biggest things here, life of the oil. Make sure you check you know how long you've been running your oil in your HDT. Check the spec sheet from the supplier. It will tell you what its life expectancy is. Keep track of that. Make sure as well that you're following the right standards. There are differences in ASTM, in the ISO, both in VICAT and HDT. You want to make sure that you're applying the right forces and you're using the right specimen and the specimen's in the right orientation. Ways to increase lab efficiency. LVDTs, have a LVDT that self-calibrates. A chiller. Having a chiller, a water chiller to help cool the bath down between tests. You can get from one round of test to the next round of test by cooling the bath quicker. You can get this down to 30, 45 minutes quicker between tests if you have a chiller. Have software that would have prepackaged test setups in it so that you don't have to go through creation of methods. You simply pick a preset method and load it and start running.
Great. Thank you, Stephanie. I know we talked a lot during this webinar, mainly Stephanie. She had most of the content here, but we did cover a lot of different standards. And here is just kind of a overview of all of the most widely used standards for both ASTM and ISO per test type that we talked about. So I'm going to linger here just for another second or two if anyone wants to screenshot this at all. But again, we cannot stress enough to be sure to read the standard fully to make sure that you're being compliant. All right. And then, like we mentioned at the beginning, this is the first webinar in a full series of webinars. Here is the schedule. So after you receive your product data sheet, what do you do next? So these webinars are going to go in more depth on each test types and applications in different industries such as automotive, biomedical, and consumer goods. So if you're interested, please scan this QR code to get more information on it. And if you want to register, you can do that through the same QR code. But thank you all so much for attending. If you have any questions, please put them in the chat, in the Zoom link, and then thank you guys so much for joining.
Nice, thank you.
All right, so don't everybody hop off. We're going to jump over to the Q&A section. And there are a few that came in, so I'm going to just fire these off, and then Sammy, Stephanie, whoever wants to answer them, feel free to chime in.
Mhm.
So we'll start with this one. So we run the same tests, but we still see a lot of variation. Where do you usually start troubleshooting that?
Yeah, so I could take this if you're running a static test. I think ultimately where you start is making sure for static tests, again, tension, specimen alignment, making sure that you're visually aligning your specimen like we talked about briefly in this webinar. I would also just ensure that you're running with powered grips. If you're not running with powered grips, maybe your operators are clamping the grips at different tightnesses, which will ultimately lead to some variability within your data. So those are the two main things that I would start with. And then again, like we mentioned so many times, read the standard, make sure you're compliant with the standard.
Okay, great. Next question. When testing plastics in tension that elongate to over 300%, what equipment do you recommend?
Yeah, so great question. So for testing intention for ISO 527-2 and ASTM D638, the two most common tension tests, they do require you to use an extensometer to record the modulus of your material, but that is only up until yield. So it is also required to remove your extensometer, whether it's physically or automatically. If it's a virtual, or sorry, not a virtual extensometer, but an automatic extensometer, you must remove that after the yield point and then calculate nominal strain. So even though your material may be elongating much further than the modulus region, which it usually is, um, that extensometer must be removed. So I highly recommend still using the same equipment that we talked about, but just removing your extensometer. You should not be keeping it on throughout the whole test.
Great. Are there workflow or software improvements that can significantly reduce operator time or testing errors?
Yeah, I think like if we look at HDTs and melt flows, certainly having a software that might have has predefined methods in it will make the test setup go quicker. That can also help with, like in the case of our melt flow testers, we have pre-canned methods based on the material. So all you need to do is go in, select the material, the standard you want to run to, and which material you're using. It walks the operator all the way through how to get the test set up and run the test. So that should help lead to some consistent results and repeatable results.
Great. We have another tensile question. How accurate is the tensile modulus data when there's not an extensometer? Is it reliable enough to make comparisons between materials, even if the value itself might not be as accurate?
Yeah, that's a great question. So it depends on your entire setup and what system you're using. Let's say you're using one of our systems with powered grips. It is very accurate. So our crosshead, I believe, for ASTM is a Class C rated extensometer. So the ranking of extensometers goes B1, B1, B2, and then C. So it's not that much of a difference between the classes. So it's definitely good to compare your data to each other rather than have it on your data sheet. So it is accurate, it's still very accurate. It's just not complying with the standard. So that's kind of where we fall into some like rough waters. It's not complying to the standard, but yes, it is very accurate and it's very okay to compare your results internally from a batch from this year versus a few months ago versus a year or two ago.
Thanks. All right, Stephanie, this one looks like it might be in your court.
Mhm.
Is there a tool that can be used to align specimens for HDT test by ASTM standards in a sideways orientation?
In a sideways orientation. Uh, yes, what we have is in the sideways orientation. So I'm assuming what you're talking about is instead of running on edge, we're going to run like ISO. So we're going to run flat. There are shoulders that allow you to align the specimen in that orientation as opposed to the way ASTM, the core ASTM standard has you set up the test to run.
Okay. I'm seeing one more question, and then we'll see if any others come in. But at what point does it make sense to add specialized equipment like fatigue or impact testers versus using a universal testing system?
I say you look at this, what's the standard telling you to use? As we noted, Sharpie and ISO standards to be in full compliance with them, you need to use a pendulum. The standard states it shall be done on a pendulum system. The high-speed puncture test, the 3763 and 6603-2, both call for the use of a drop tower with systems to measure velocity and report load. So I would say if you are wanting to run a test, I look to the sheet. I would look to the standards. Somebody's going to tell you what standard they want you to run at. Or the other option is, what are you trying to, if it's a finished component or something, what is the real life event you're trying to duplicate? And that will guide you as to which piece of equipment you may want to consider using.
Okay. I believe that's going to wrap up our Q&A session. So now I get to go through my wrap-up notes. So if anybody sends any questions while I'm doing this, I'll make sure to get those over to our presenters, and then they're just going to follow up by email. Reminder, this was recorded, so I will follow up with emails. Anybody that attended or registered will get a copy of that. And as we see on the screen, we do have a bunch of other webinars coming up. We actually have a really nice landing page that goes through all of the plastics testing webinars that are coming up. So if you want to see all the descriptions in one spot, the link I just put into chat will be the best spot to check out. And then finally, you're going to see a brief survey when the webinar ends. We would really appreciate your feedback. And so with that, thank you both for presenting. And of course, thank you all for attending. We appreciate your time. Take care, everybody.
Thank you.
Thank you. Bye-bye.